Okay, we started by talking about pseudo-inverse, and we start to see that why we need pseudo-inverse, because not all the matrices or vectors that we want to find is inverse is squared, or if they are squared, not necessarily they are non-singular. And then we talk about the geometrical representation of them. We said, for instance, if we have three equations for two unknowns, then in such case, we call the system of equation to be overdetermined. And we draw and we saw that the intersection is happening actually at 3 points. And what pseudo-inverse tries to give us is the point which has the minimum distance from all the intersection points. Now, let's start by writing a few theorems and properties which we need to know them in order to proceed further with examples. Consider A be from X vector space to Y vector space. We define a linear transformation NA orthogonal complement to RA, where Tx is equal to Ax for any x belonging to NA orthogonal complement. Then T is bijective. What's the meaning of bijective?
Oh, it's both.
Yeah, it's one-to-one and onto. If it is one-to-one, what does it mean?
That each element has only
NA is equal to
0.
What was the term that we use for NA orthogonal complement?
Range, we can also...
No, this is range. Or codomain. What's this? This is our domain.
Domain, yes.
This is our domain. This has a proof. I recommend you read page 24 of our book for the proof of this. The proof is not necessarily important for our aim, but it's good to see. Because we want to use this, so that's why we have written. With A and T as defined above. Okay? As defined above. We define transformation A pseudo-inverse to be from Y vector space to X vector space by A plus Y is equal to T inverse Y. Now, one thing that I want you to notice is T is bijective, one-to-one and onto. What does it mean if it is one-to-one and onto? If it is one-to-one and onto, it has one very important property that we knew it from before. Look here. It has an inverse. It has an inverse. Whereas A, we don't know. It has a pseudo-inverse, but we don't know if it has an inverse or not. But the pseudo-inverse is defined in such a form. and this is y1, not y, where y is equal to y1 plus y2 with y1 belonging to range of A, because we are going from our T is from NA orthogonal complement to RA. In other words, our range, the Y that we are using here, should belong into here. Otherwise, we cannot calculate it. And Y2 belongs. Okay, where Y2 should belong to? You know what does this mean? Look, this means that this means that there is sets of vectoring here which I can define in a form that my linear transformation is bijective, so I can have the inverse. In other words, it's a square, it's not singular. So a subset of it. So and we can define in that form. So if y1 belongs to RA, where R2 belongs to?
It has to belong to RA2.
RA2.
No, RA2.
Then how can we find what is y1, what is y2? You know, y1 is symbolically show all the vectors in RA which are satisfying this condition. In other words, they actually satisfying this condition for the T. So y2s are not satisfying these conditions.
Yeah, so it's probably going to be A orthogonal.
Exactly. Complement. Orthogonal complement. And then A plus is called the pseudo-inverse, the more Penrose pseudo-inverse of A, which has been defined in 1955. Like 60 years ago. Here. If you remember from undergraduate algebra, we had a definition for A inverse in this form. We said that B is A inverse if and only if we had B multiplied by A is equal to A multiplied by B is equal to R, right? So, and we had maybe this type of questions that your teacher were giving you a matrix and said that proof that this matrix, even if it's a symbolic matrix, is the inverse of another matrix. And how we were proving it, we were checking these conditions. We were multiplying and we saw that if it is I or not. So we have the similar thing in order to see if something is the pseudo-inverse of another vector or matrix. There are 4 conditions which we have to check. So, let A belongs to R, M, and R. Then G is pseudo-inverse of A, is A plus, if and only if P1 AGA is equal to A, P2 G A G is equal to G. P3 A G transpose is equal to AG. P4 G A transpose is equal to GA. And actually, if all these four conditions is satisfied, then we can write one more strong statement. Then A plus always exist and is unique. If we have only P1, P2, P3, we have right inverse, pseudo inverse, and if we have only P1, P2, P4, we have only left pseudo inverse. So if we have only P1, P2, then we have not a unique pseudo inverse. How we are using this theorem is as follows. Consider A to be 1, 2, a column vector. Verify directly that A plus is 1 over 5, 2 over 5. Please verify it. How do we verify? We write A plus A, we check if it is A. We write A plus A plus, we check if it is A plus. And then we need to check also P3 and P4. P3 and P4. Please do it and let's see. Meanwhile, I have just uploaded the assignment for the homework 3. So your 2 weeks start from today. But I think you should do the homework before 2 weeks, as we have the midterm exam before the deadline of the homework.
So are we going to have homework 4 before the midterm?
Depends. I mean, if I finish this chapter, which with high probability I do, then we will have homework 4. Before the midterm, I will try to have one practical session, a problem solving session, and I will solve some other questions which are not assigned to you as an homework. today we will also learn that in general for such a column vector, how we can calculate the inverse, the pseudo-inverse of the vector. And when you have, just keep in your mind, when you have an overdetermined equations, system of equations, it is good when you find the results, put the results back into the equation and check how close you are to the answers that you were expecting to see. If it is very varying, maybe you want to use another method than the pseudo-inverse in order to solve it. Alright, did you check all the four?
First three.
Okay, do the last one, then come and solve it on the board.
So we're just verifying then. We're just verifying these.
Yeah, just verify all of them.
Basically multiplication.
Yeah. One divided by 2?
Sorry.
But I mean, in general, we know that you have to write in a more clear form. Like from middle of nowhere, you shouldn't put 1, 2. I mean, you have to write in a... Okay, continue. I mean, you have to write in a more clear form. 45? When I'm checking, instead of 25 points, I can write 2.5 and then I tell you just. 1, 2, the tick. Very good. What about 3 minus 1? Do it at home, and then you will see that this is left inverse, which means that it will satisfy only P1, P2, and P4. Any question about this solution? It was pretty straightforward, right? Yes, sir? So now we start by doing some more mathematical definition of how to calculate the pseudo-inverse. And it's a theorem. Let A belongs to R m by n with rank R, then actually A plus is being calculated as a limit of delta goes to 0 for A transpose A plus delta square I, which has an inverse, and A transpose, which is equal to limit of delta goes to 0 of A transpose multiplied by A transpose plus delta square I inverse. Now let's spend a few seconds on this formula. A is not an S-square matrix, right? A is not an S-square matrix. But this is S-square, right? Now, A transpose A will make it to be an n by n matrix. A transpose is making it to be m by m matrix. So we understand that these two i's are not of the same sizes. But my question is that why do we add the delta I to our matrix? What is the meaning of rank R? And we know that if R, because we are talking about the general form, R can be less than the minimum of M and N. So what does it mean? It means there are some columns, rows, which are linearly depending on the other ones, right? Which means that they can be produced. And this is actually a reason that even if M and N were equal to each other, causing the matrix to be a singular matrix, right? Because it makes the determinant to be 0. In order to make sure that there is no linear dependency, we are destroying it by adding different, same value but on different elements of this square matrix. In other words, we cannot have now the linear dependency between the rows or columns. Okay? Now, what happens? We want to calculate this limit and make the delta goes to 0. This is not an easy way of doing the calculation in general, but it has some cool properties which we want to use there. Property 1. A plus is A transpose multiplied by A transpose inverse if A is onto. What does it mean? it means this. We have, it's, do you remember what it means by onto also? We are right inverse, right? When we have independent rows and we have right inverse. This is then, but by we have it means that A has right inverse. So let's see the second one, which we might be able to guess what the second one is. A plus is A transpose A inverse A transpose. If A is 1 to 1, so what do we understand from this? We have column, this time independent, independency, and A is left invertible. Three, for any scalar alpha, alpha plus is Donna, for any scalar alpha, what is the pseudo-inverse of that scalar? Very difficult question.
One over alpha.
1 over alpha, Hassan, do you agree? 1 over alpha, Ike?
Yeah.
It's 1 over alpha if alpha is not 0, because in case of 0 it's not defined, and if alpha is 0, it's 0. Fourth one, for any vector v belonging to Rn, which is a column vector, v plus is v transpose v plus v transpose, which again we have a pseudo inverse inside it, which is not very easy, but we have a very easy result. It's v transpose divided by v transpose v if v is not 0, and it is 0 if v is equal to 0. Previous example that we had. Remember this is a scalar, this is a number. Previous example, A was 1, 2, right? Was 1, 2. Let's see that how we calculate A plus. A plus is V transpose, which is 1 and 2, divided by V transpose multiplied by V, which will be 5. So it will be 1/5, 2/5. In the previous example, fifth, good properties. 1, 0, 0, 0 is a very well-known singular matrix whose pseudo-inverse is 1, 0, 0, 0. And similarly, 0, 0, 0, 1, pseudo-inverse is 0, 0, 0, 1. However, I want you to keep this one in your mind. If this one was alpha, then this would be 1/alpha. I mean, if you want to generalize it. Similar thing is valid in here. If it is alpha, this is 1/alpha. Sixth one. If we have the 2 by T matrix of ones, the pseudo-inverse is 1/4, 1/4, 1/4, 1/4. Of course, you can always have a computer and calculate for you, but some of them are just so simple, so you can keep it in your mind. Seventh one is 0, 1, 0, 0 plus this is equal to 0, 1, 0, 0. So you understand that 0, 0, 1, 0 plus is 0, 1, 0, 0. And similarly, so that formula that I wrote, the limit, is not a very easy formula to calculate, but we have series of very cool properties which we can benefit from those properties. And I think the most frequently used property which you need to know it is the property number 4 for the column vectors. Now, we will talk about 2 theorems. The proof of the theorems, I will give a hint about it. But the reason that we are studying these 2 theorem is that in the next chapter we want to talk about something which is called singular value decomposition, which is a very, very important concept, especially it has lots of usage in computer science. And when we finish that chapter, we will get back to these 2 theorems, and then by using what we have learned and these 2 theorems, we will see how we can calculate A plus. Actually, this is how MATLAB calculates the pseudo-inverse. It uses singular value decomposition in order to calculate this A plus. So right now, we just simply write the theorems, and I give you a guideline how to prove it. But we keep it in our mind because later we will get back and use them. And we do a numerical example by the end of the next chapter using these theorems. The first of those theorems are, let A be an n by n matrix in R, and suppose U is R m by m, and V is in R n by n, and are orthogonal.